Turn on the laser. Great. So hello, everyone. Thank you very much for coming to my talk. My name is André Melo, and today I'll be talking about work that I did together with Valla and Fatemi, who is the postdoc at Michel Devray's group at Yale, and Anton Akhmerov, who is my supervisor, and we're both members of the Quantum Thinker group in TU Delft. So the preprint is out on arXiv. It's called Multiplet, Supercurrent, and Josephson tunneling circuits. And let me just brag for a bit and say that if you're interested in running the code and seeing how we produce the results, you can. We publish the source code as well. So if you want to play around with parameters and do your own simulations, feel free to check out the Zenodo repository. Okay, so let's get started. And I want to begin by briefly reviewing the physics of SNS junctions and Andreev reflection. So to start, let's imagine that I've taken a piece of metal and connected it with a piece of superconductor. And now I want to think about what happens if I have an electron traveling in this metal towards the interface between the two materials. And I want to say that this electron is traveling at energies below the superconducting gap of the superconductor. So once it reaches the interface, it has to do something, right? It cannot just propagate as a single particle in the superconductor because there are no available states in the superconductor below the gap, single particle states. So it has to reflect. It can, of course, reflect just as an electron, so basically bouncing off of this wall of sorts. But it can also undergo a more interesting process, which is called Andreev reflection. And the idea there is that the electron actually retroreflects as a whole. And now if you count the charges in the beginning and end of the process, you had a -1 charge in the beginning from the electron, and you have a +1 charge at the end. So that means that there's a 2e difference. And what happens is actually that a Cooper pair was created in the superconductor in this process. So essentially, this electron goes into the superconductor, but drags along another electron from the metal and creates a Cooper pair that joins the condensate of the superconductor. So that's Andreev reflection in a nutshell. Now, if I put together an SNS device, meaning superconductor, normal region, a short normal region, and another superconducting terminal, this Andreev process can still happen. Meaning I can still have an electron traveling that retroreflects as a whole. This whole then goes to the left. Andreev reflects as an electron, and the whole process starts over again. So these successive Andreev reflections can become sort of resonant and form a bound state that lives in the junction here, in this weak link part of the device. If I were to plot what the energies look like of the energy eigenstates in the system, they would look something schematically like this. So this is energy, and this is the superconducting phase difference across the superconductor. So each superconductor has some phase, and the spectrum of the system depends on the phase difference. So, I have above delta, I have the continuum quasi-particle, the quasi-particle continuum in the superconductor. Below the gap, I have this special subgap state, this Andreev bound state, that kind of disperses with the phase difference. And the special thing about this state is that it can actually carry DC supercurrent across superconducting terminals. Because remember that each of these processes is transferring charge from one place to another. So this is known as the DC Josephson effect. It's a very famous and important effect in these junctions. Now, so far, I've only told you about a local process that happens in these devices, right? So a process that involves just a single interface at a time, or a single terminal at a time. But there are also non-local processes that can happen that involve multiple contacts or terminals at a time. And one famous example is a process called cross-Andreev reflection. The idea there is the following. Suppose you have now, instead of SNS, you have an NSN device. What can happen is that you have a Cooper pair in the superconductor that breaks apart and sends an electron to each metallic contact. Now, the inverse process is also allowed. You could have an electron that's traveling towards the superconductor, And normally in the normal Andreev reflection, it would drag a partner electron from the same metallic part, but it can actually also drag an electron from the other metallic contact. So that's why it's known as cross Andreev reflection. This sort of device is known also as a Cooper pair splitter, and people are trying to use these kinds of schemes to reliably produce entangled electrons. Now, there is a thing about this process, which is that it is a delicate process in a sense, and that is because, as I described it here, there has to be coupling between this metallic contact and this one. So somehow these contacts have to couple across the superconductor. But the problem is that the electron wave functions decay exponentially into the superconductor with a decay length that is called the coherence length. So that means that if I make the superconductor very wide, much wider than this coherence length, the wave functions decay, way before they can reach the other contact, and there's essentially, you kill this coupling between the contacts, and this cross-Andreev reflection process is suppressed. So that means that this process is somewhat fragile, or you need to be aware of the length scales in your system and tune your device accordingly. Of course, you can still have, now that you have this device, you can still have local Andreev reflections happening. So you can still have current flowing into the device, but just not through this non-local process involving these two terminals. Great, so that was a brief recap of SNS junctions and Andreev physics. And now I want to kind of set the stage for the question we want to ask, which is the following. So we saw that Josephson junctions can carry DC supercurrent at 0 voltage through these Andreev bound states. But what about at finite bias? So if I voltage bias my device, can I still get a DC supercurrent? The answer is in 2-terminal setups, no. So in an SNS junction, you cannot. And that is because when you apply a voltage in SNS junction, now charge transfers across this junction costs some energy. And in order to have supercurrent, you actually need a process that displaces charge from terminal to terminal without costing any energy. So in 2-terminal devices, no luck. You can, of course, still have AC supercurrent. That is the kind of the dual of the DC Josephson effect. It's called the AC Josephson effect. Or you could have dissipative DC current. That's through something like multiple Andreev reflections. But you cannot have DC supercurrent in an SNS junction at finite bias. So kind of the natural follow-up question is, okay, it doesn't work in 2-terminal setups, but what if we add more terminals? What if we attach a 3rd superconductor, for example, or a 4th? And there, the answer is yes, it actually works, provided that you apply commensurate voltages, meaning that the ratios of the voltages are rational numbers. And as an example, let me show you what happens in a 3-terminal device and how you can get supercurrent at this finite bias. So here, let's consider a device that is now S, N, S, and S. So we have 3 superconducting terminals, and this middle superconductor is grounded. Now, it turns out that if you bias the left and right superconductors according to this expression, so NV1 plus MV2 equals 0, where N and M are integers, then you can actually transfer N plus M Cooper pairs to the central superconductor at no energy cost. And to see this, note that this is actually, or previously we said that in order to have supercurrent, we need a process that moves charge without energy. So actually, that's exactly what we're demanding with this condition here. On the left-hand side, we have the initial energy of the state of the system. So we have N Cooper pairs in the left-hand side and M Cooper pairs on the right-hand side. So the initial energy is like 2E NV1. So I've cut off the 2E here, so just an NV1. And the energy of the electrons or the charge on the right is mv2. The final energy is 0 because I transferred the charges to the central superconductor, which is grounded. So this condition is exactly demanding that we are demanding that there is such a process that transfers this charge without costing energy. The sort of simplest or lowest order non-trivial process that can happen is the quartet supercurrent. And that's when n and m equals 1. So each biased terminal transfers 1 Cooper pair to the central superconductor. And I should note that from now on, and also in the paper, we focus on the quartet case just for simplicity, but like all the math that we do, all the results, you could do exactly the same thing for higher order resonances or other multiplets, so other combinations of n and m. But for simplicity, we focus on the quartet supercurrent case. So microscopically, how does one explain this? How does this come about? Well, let's again imagine that we have an electron traveling in this metallic region towards the central superconductor. This electron is going to go towards the interface, is going to cross Andreev reflect as a hole to the other side. This hole is going to travel to the right to this other biased contact, and it's going to Andreev reflect as an electron. The electron again goes towards the middle, cross Andreev reflects as a hole. This hole on the left, Andreev reflects as an electron, and now you're back to the beginning of the process. You just repeat this process. This is kind of the microscopic steps that lead to this charge transfer. And to see that I've transferred 4e to the central superconductor, let's just count the charge transfer processes. We have 2 crossed Andreev reflections that happened in the middle superconductor, and each of those transfers a Cooper pair. So that means that we've transferred 2 Cooper pairs or 4e to the central superconductor in like a single coherent process. So microscopically, up until now, this is how people have explained and have proposed to realize these multiplets experimentally. And in fact, there have been a number of experiments that have looked at these types of devices and found convincing evidence of these multiplets. Here I'm showing a data set of one of the most recent experiments, I believe. I think this is a 2016 paper. And on the left-hand side, I'm showing you the device that they patterned. It's exactly what we were looking at, S, N, S, and S. The superconductors are in blue. And then what they do is they take this device and they bias the left and right superconductors and just measure conductance. And what you find is that if you look, so here this color map is conductance, and the axes are voltages, VL and VR. And we find, for example, a resonance. We find an increase in the conductance exactly at VL equals minus VR, which, if you remember, was exactly the biasing condition for quartets. So great, we did this experiment. We found an enhancement in conductance where we expected it. They also see higher order resonances. You can check out the paper to see the full data. But the quartet one is the most visible here. However, there are a couple of problems with this sort of setup. The first is that, first of all, you only see a small enhancement of the conductance. So if you notice here, if you look at the scale, actually the enhancement at the quartet biasing condition is not very high. So the supercurrent is not very super, let's say. And this is due to, we think, high dissipation in the normal regions of the device. And secondly, the constraints that I talked about of needing to take having tight control over the microscopics of the device, over the electronic states of the device, still apply. So it's non-trivial to engineer this type of device. It requires precise control. And so this is kind of the background. The background when we started the project, when we started thinking about does multiplet supercurrent actually require this Andreev physics? Or is there some sort of other process that could mediate these multiplets and maybe alleviate some of these experimental hurdles? And we got started down this line of thinking because of a pair of papers that came out. So in 2015, I believe, there was a paper that came out called Multiterminal Josephson Junctions as Topological Materials. And the authors here had a very, very nice idea. They discovered that if you take a central scattering region, a normal metal, for example, and you connect it to superconducting leads, this sort of device can emulate topological band structures. So you can essentially make a topological material out of these things. And the way to think about this is the following. So this structure will have some energy levels, and those energy levels will depend on the phases of these superconducting terminals. But they have to depend periodically on these phases. So you can kind of think of the energy levels as your bands and the phases as some quasi-momentum degree of freedom. And so effectively you have a sort of a band structure in this device. And it turns out that you can, what the authors show is that you can engineer this scattering region such that you get non-trivial band topology in the system. And this manifests in a number of ways, like quantized conductance and stuff like that. So it's really a very nice idea, but it does suffer from the same kind of hurdles that I was just explaining. And so last year, another paper came out called Valla Josephson circuits, where Anton and Valla are co-authors. And they were thinking, okay, could we somehow encode this physics in different degrees of freedom? And what they found out was that actually, if you take tunneling junctions, so instead of now having SNS, you have SIS junctions, so superconductor, insulator, superconductor. You can actually encode the same physics in the collective electronic modes of this device. This is a somewhat subtle distinction, so that here on the left-hand side, we are encoding the physics in the Andreev or fermionic degrees of freedom of the weak link. But here on the right-hand side, actually, we have kind of a circuit QED sort of setup where, you have some electronic modes in this circuit, and actually we're looking at fluctuations in the phase degrees of freedom, the charge degrees of freedom of the circuit. And these are bosonic excitations. It turns out that you can encode the same sort of topological physics in these degrees of freedom. And this is nice because these devices, as I mentioned, these sort of tunnel junctions are kind of ubiquitous nowadays because they are the building block of all sorts of CQED devices and other superconducting devices. So they are relatively easy to make and measure in the lab. So effectively, this proposal kind of removes some of the experimental hurdles that this proposal had, which is nice. And so we started thinking, what if we do the same thing, but with multiplet supercurrent? We just steal from fermions again and somehow encode the same physics in bosons. And so we thought, okay, what is the simplest tunneling circuit that could, in principle, support multiplet supercurrent? And this is what we sketched, or I should say Anton sketched. And the idea is the following. So we have three terminals, because again, we need, for this multiplet, we need three terminals at least. And so we have the left terminal, right terminal, and the grounded terminal, and a central superconducting island. And this island is connected to all terminals through a Josephson junction. And also we've added here a capacitive element here, some charging energy to the superconducting island. And the reasoning there is that if you don't have capacitance, if you don't have a charging energy, your circuit is in a sense boring because it's not really quantum. So the Hamiltonian is then diagonal in the phase basis. So you don't really have any fluctuations in the any quantum fluctuations in the phase degree of freedom. So we thought this would be boring. We'll see that's not exactly the case. And so that's why we added this charging energy in the beginning. This is the thing we decided to start with. And just as a reminder, these are all SIS junctions. So only local tunneling processes here are allowed. So you can only transfer charged, Cooper pairs across the junction, single Cooper pair transfers. All right, so we have a proposal. How do we actually check if this carries multiplets? Well, there's a simple recipe to do that. And to start out with, we analyze the circuit in the zero charging energy limit. So we set this EC to 0, or equivalently, we just remove this part of the circuit, this capacitor. And we're going to compute the current that's flowing into ground. So how do we do that? Well, we compute the adiabatic current phase relation, so the kind of the instantaneous current flowing to ground at some fixed phi 1 and phi 2. And you do that just through basically diagonalizing the Hamiltonian and taking some derivatives. And you find a current map that looks sort of like this. So at some choice of phi 1 and phi 2, I have some current flowing to ground. But now we want to voltage bias the circuit. We want to see what happens if we, for example, bias the circuit in the quartet biasing condition that's with V and minus V. Do we get quartet supercurrent? Well, when you do that, your phases are going to wind linearly in time. So phi 1 is going to go as, for example, Vt. So we're going to wind with a rate that's proportional to the voltage. And phi 2 is going to evolve in time like this. So there's some phase offsets. This is an important parameter that I'll talk about in a moment. So there's some phase offset relative to phi 1 minus Vt. This is exactly the quartet condition, plus V minus V. So this means that the phases are going to follow a line, right, in this phi 1, phi 2 plane. So what we have to do is essentially, track the current along this line and see if it has a finite average. If it does, we have a current flowing to ground. And so this is exactly what I'm plotting here in this inset here. I'm showing the current along this particular line for some choice of offsets, and the dashed line here indicates the average. So you see that it does have a finite positive average, meaning that we get quartet supercurrent. And actually, if we did not have this commensurate condition, so if, for example, let's say phi 2, the voltage on phi 2 was like pi times the voltage on phi 1, then what would happen is that these phases actually would sample the whole voltage plane. They would not be following a line. And there, if you do that, you average to 0. You have 0 net current flowing. So this is really the multiplets that we were looking for, in a sense, because they only appear at these commensurate conditions where you follow a line that can have a finite average current. So you can play the same game for different offsets and find a current phase relation as a function of the offset phase here, and we find kind of what you would expect, just a sort of near sinusoidal phase relation. Now, the other thing to say here is that, again, just to remind you, this is at zero charging energy. And this is a bit surprising to us because we thought zero charging energy means the circuit is boring. But it turns out that even this circuit already carries multiplet supercurrent, which is quite nice. So what happens now if you add a finite charging energy, if you allow finite EC? Well, there, what you find in the general case, if you compute this instantaneous current map again, you see sort of a similar dependence, but with an overall decrease in magnitude. So at some arbitrary finite EC, you will still have a multiplet supercurrent, just at a reduced magnitude. But there is an interesting effect here, which is the following. So So there's an additional parameter related to this charging energy, which is the offset charge of the island. Now, if we are at this parameter is called ng, so if we are at ng not equal to 0.5, for example, 0.4, let's say, then the charge states in the island are non-degenerate. And so that means that as we increase the charging energy, this difference between the 0 and 1 states increases arbitrarily, and I have to pay a very large energy in order to transfer a charge into the island. And that means that the current is gonna vanish and the EC goes to infinity limit. And that's what I'm plotting here. So here I'm plotting the maximum quartet supercurrent, so maximum over all offset phases, as a function of increasing EC. And the blue line is at ng equals 0.4. So there's nothing special about this value other than the fact that it's not 0.5. And what you see is that as I increase EC, the current just goes to 0. And that's because, again, the cost of adding a charge to the central island just becomes prohibitively high, and I just suppress this multiplet supercurrent. However, there is a special point, and that's the charge degeneracy point, this 0.5, where the 0 and 1 states are actually degenerate. And in that case, I have the orange line, where what you see is that the supercurrent plateaus to a constant at infinite EC. And this is quite neat because it says that even at arbitrarily high charging energies, where you can only have like one Cooper pair hopping into the island at a time, so in a Coulomb blockaded regime, if you want, this multiplet supercurrent still flows. So these are processes that transfer several charges at a time to the ground node, but they are mediated only by single Cooper pair transfers. So this was quite surprising to us as well. And in the paper we do some analytics as well. In this high EC limit, you can actually write down an effective 2x2 Hamiltonian, and we show that the numerics converge nicely to the values you get from the analytics. Finally, final thing I want to show you is another contribution that we computed to this quartet supercurrent or multiplet supercurrent. So the currents that we have been looking at were computed in the adiabatic approximation. But the leading order correction to that is a current that's given by the Berry curvature of the ground state of the system. And you can show that it looks something like this. So there's some constant, then it's proportional to the Berry curvature, omega 1, 2, we're calling it here, times the voltage. So this is the instantaneous current at some choice of phases phi 1 and phi 2. So now we play the same game as before. We have some instantaneous current. We know that the phases are going to follow a line in this phi 1, phi 2 plane. So we're just going to have to average this Berry curvature over that line and see if it's finite. If it's finite, we have a contribution to the supercurrent that comes from the Berry curvature. And again, we show that in the general case, this is a finite contribution. So here I'm showing an example where we I forgot to show the plot that has the actual data along this cut, but it is a finite average of the Berry curvature along this line, which means that we have a geometric contribution to the multiplet supercurrent. The neat thing is that this contribution scales linearly with the voltage. So in principle, it could be distinguished from the adiabatic contribution. The adiabatic contribution has no scaling with the voltage. So in principle, this could be an experimentally feasible way of distinguishing between the two. And you could kind of even think about, can we design a circuit that maximizes this geometric contribution of the multiplet supercurrent so that you have, Berry curvature only multiplets. And that would be a cool extension. That was the final thing I wanted to show you. I just want to summarize and give you take-home messages. So what we show in this work is that tunneling Josephson circuits also support multiplet supercurrent, but without any Andreev physics. So actually only through collective excitations of these electronic modes. The neat thing about using these circuits is that they're very standard nowadays. So you could make these things in the lab tomorrow, in the sense that there's nothing esoteric about these circuits. They're very standard building blocks of CQED. And we highlight three contributions, three kind of distinct regimes, if you want, of this multiplet. So we show that a classical circuit with no charging energy is capable of carrying multiplets. If you add quantum fluctuations from charging energy to your circuit, you still carry multiplets. And in fact, there's an interesting regime where you can get multiplets carried only by single Cooper pair transfers. And thirdly, we show that there's yet another contribution that comes from the Berry curvature, so a geometric contribution to the multiplets. In terms of further work, there's a lot of possible directions, but perhaps the most exciting is whether we could come up with a way of coherently controlling these quartets. And the reasoning there is that there's a lot of work being done both by theorists and experimentalists to try to realize these cosine 2 phi Josephson junctions, which are junctions where only two Cooper pairs, the lowest order charge transfer is of two Cooper pairs, as opposed to a regular cosine phi junction. And this is exactly quartets tunneling across the junction. So if we could coherently control these quartets, we could, in principle, make a cosine 2 phi junction. And people are excited about those because they allow making these protected qubits. So that's one possible direction of future research. So that brings me to the end of my talk. I want to thank you for coming, and I'd be happy to take any questions you might have.